Okay, let me just look. Okay, no. Let me just reset now. Okay, last time let me just look at the notes a little bit. The principle of operation of the deduction machine, the three-phase. Um, the three-phase induction machine, it uses the Faraday's law and Lorentz law for force. So whenever three-phase supply is given to the armature stator, a rotating magnetic field is produced. This magnetic field is rotating in the space electrically, and if the rotor is placed in this magnitude of a magnetic field, then an EMF is induced in the conductor rotor. Since the conductor is short-circuited at the ends, therefore the current is produced. So whenever there is a current and a magnetic field, there is a force, Lorentz force, which tries to rotate the conductor, and a torque is produced. So in this way, that electrical energy is converted to mechanical energy. So we came up with this equation last time, but we can just look back and see that suppose we have a two-pole per phase system, and 360 degrees revolution in t seconds is almost 1/f seconds. That is now time. The equation here is just like saying that one revolution is in t seconds is equal to 1/f. So in 60 seconds, that is 1 minute, it is 60 of 1/f. So per second is 1/f, that's frequency, but for 60 seconds, it is 60 of 1/f. So it is just 60f. The f will multiply 60. The f will multiply 60, and we shall have 60f revolutions per minute. That is now the synchronous frequency of the stator. And for one pole per pair, one pole pair per phase, which is almost 2 poles per phase. So let P be the number of poles per phase. Then NS will be 2 times 60F over 2 for 2 poles per phase. So NS is supposed to be 120F over P for P number of poles per phase. So it is for 2 poles, it's going to be 2 times 20F over 2, because now it is 2 pole per phase. But when it is N, this will cancel out maybe for 2. But 2 pole, no, P pole for P number of poles per phase is going to be 120F over P. So this equation, one single pole is almost like, because you have the north and south, is 2 poles per phase, and will cancel out in that manner. And that is for single pole. That is for P poles is going to be 120F over P. So we can roll down and see a few things here and there today. I want us to go back to the equivalent circuit. We mentioned it at the time. The equivalent circuit of induction motor. So induction motor equivalent circuit for the stator. For the stator, the stator is the supply of the rotor, and it is going to generate an EMF, given that the voltage E is being supplied from the system, and it has some reactances. This is for magnetization, and this is for the system current which is flowing, and we shall have the output of that current to be E1. And the rotor, which is sorted at the ends, it has a resistance R2, and is rotating at the frequency of SF, and you also have a reactance of JSX2. So this is the actual rotor circuit. So at the running speed, at the running time, this is what is supposed to appear. So these notes, I'll send it to you so that you can analyze it properly, so that you can understand how it looks like. But this is the comparison between the stator and the rotor circuit, which is sorted at the ends. So you'll find that at standstill, this diagram is more or less, will take a lot of our time because of the phasor diagram, which may not be very easy to explain now. But I just want to take you through so that you understand that we need to analyze the circuit diagram for both the stator and for the rotor, which is almost like the one for the what do you call it, the transformer. So we can even see here the comparison between induction motor and the transformer. So this is the rotor and the air gap, and this is stator. And this is the primary part, of the where the supply is, the three-phase induction motor. And this is a secondary part with the mechanical load. So we'll find that if V1 is the supply voltage or the starter terminal voltage per phase, the starter resistance will be this one. And also the starter leakage reactance per phase, which is this one. The supply current at that point is I1 per phase, because we are dealing with this is just per phase. There are three phases. There's a three-phase, and I1 is supply current of the step per phase current, and E1 is induced EMF, the one we are referring to. So V1, normally the supply itself is going to be the induced voltage plus that current, which is going to be useful for the system, which may not be used for the system, but it's going to be the losses of the system due to the self-induction of the system. So the stator equivalent circuit now, our primary side is this one, and the secondary part is this one with the slip. So at no load, it means that okay, this is just for any slip. At any slip, this is a diagram, but I note is the no load current per phase. When the motor has no load, it doesn't really rotate to run any load at the end, or maybe connected to the shaft. But this is a working iron losses. This one in the transformer. So this circuit is very clear to understand. So the starter circuit or equivalent circuit is this one here. And this one we analyzed it at the time in our diagram. And we said that these things are there. And when there's any current that is flowing, it is being supplied by SE2, which is the running voltage, supply voltage at the running rotor, and is going to be taken up caused by this R2, which is the rotor resistance, and SX2, which is the reactance of that rotor. And what is B supposed to be? So the rotor resistance in the above question has two components. The first is R2, is the rotor resistance itself and represent the rotor copper losses. The second is R2 into this S1, S over N, and 1 over S minus 1. So it is also the mechanical load on the inductor motor, which is represented by this. Mechanical load is R2 into 1 over S minus 1, because S is varying, but the smaller the S, the greater is what the load, what the rotor can run. So S would be almost very small, so that this equivalent, this bracket value can be almost closer to RL, so that the motor can have a better load to manage. So for transformer, this is equivalent circuit when it looks to, in terms of induction motor. We have V1, which is creating E2, no, E1, and E1 is creating E2. And now we can feed in the load, which is variable based on the slip. So if there's something called secondary referred to the primary. So all of this section here is referred now to this side. We can refer, we don't have the transformer equivalent, the transformer part here, but we take all of these elements here to this side. So I1 will be generated to I2 prime. So we shall have the reflected value, which is now here. This one changes to that. X2 changes to X2 is a prime reflected to primary, and R2 over S is R2 prime over S reflected value. So it will remain the same like this, and we can use it to analyze our figures, our equations. So last time we can even say that the power relations of equivalent circuit to induction motor. So the rotor or the starter input power, the P input, which is a three-phase. The stator copper losses is powers copper, which is normally I squared R, but in the three-phase it is 3 times. Rotor input power, the power that is now fed to the rotor, is now 3 times the reflected power and current, and reflected. This one, it doesn't get reflected back, but it's the same thing. The rotor resistance over S. So it is down by S. The copper losses, rotor copper losses, is 3 times the current reflected to the secondary squared, then with the rotor resistance, or copper loss in the rotor is SP rotor. So it is this one, is this value multiplied by S. So total mechanical power developed by rotor is given as P mechanical and we said that that R2 mechanical is this one. Let's insert somewhere there, not really. The mechanical load, that to mechanical is this one. So that is what is here. So total mechanical power developed by rotor is this value, or mechanical power is rotor power minus copper losses, which is this value minus this value, and you get that value now. So the total gross torque developed by rotor, the turning power, is torque TQ or TQ gross, which is the power of the rotor divided by the rotor frequency in terms of this omega s is rotating frequency of the rotor, which is this one now. And normally is given by, if you simplify this value by dividing all this by 62 pi and everything, you get 9.55 into this equation here. And you'll end up getting 9.55 the power of the rotor over ns, where ns is the synchronous speed of the system, of the RPM. So this is approximate diagram for the reflected power. The analysis is done using this equivalent circuit of the rotor, of the motor itself. And this is for the magnetization, and this is just the equivalent diagram for the resistances and the load. So the load is always, you can vary the load or the which is running the motor. Now we can look at some of the problems that may arise. I want you to, I'll send you this note so that you can know how to get the equivalent phasor diagram at standstill. The mechanical speed is 0. Rotation is S is 1. When S is 1, the rotor doesn't move at all. So this phasor diagram is good for you. The at full load slip is at full load slip. I don't know whether it's putting a tick there, but it's varying. It's variable. This one is slip is variable, and mechanical load is variable. So we can have all of them in front of secondary, and then we can get them differently. Now, let us just look at, I think we did this kind of arrangement, but now we can look at one question here. A 50 hertz 8-pole induction motor this equation here. Okay, a 50 hertz 8-pole induction motor has a full load slip of 4%. The rotor resistance per phase is 0.01, and standstill reactance is 0.1 ohms. Find the ratio of the maximum to full load torque and the speed at which the maximum torque occurs. So we shall have the the equation for the full load, torque, and ratio to maximum torque. I think this one we did it in this place here. We had the ratios, maximum torque ratio, the ratios. The torque ratios. The full load torque to maximum torque was this value here. You can see this SM squared plus SF, this SF here, 2SF SM divided by SM squared plus SF squared. That is the ratio of the torque full load over torque maximum. In this diagram here, it is a little bit different. They have changed everything to certain values here. So in this case, let's just look at this, how it is done in this kind of arrangement. So if A is R over X, the ratio between the resistance and the reactance, so we get 0.01 divided by 0.1, you get 0.1. So it's the same as the ratios of two, you can use the reactances and the resistance. So it is twice A, this A, 0.1 times the slip in percentage divided by A squared. This A squared plus the slip squared. So you get 0.69. And when you get the reciprocal of the sum, which is almost what is required here, you get 1.45. That is. But what is it that looking for? They're saying that find the ratio of the maximum load to the torque, full load to the torque, and the speed at which the maximum torque occurs. So it is 120 F over P, which is 120 times F. This is NS now. Then mechanical is 1 minus 0.1 times 750. What is this? What is 0.1? That is the slip. So normally rotor rotates a slip frequency. So it is lower than this. The speed of the rotor is lower than this by this percentage, by 0.4%. So the power flow equation of diagram is very useful. In the exam, it's good to draw this power flow equation with almost 1, 2, 3, 4, 5, 6 elements which are being considered. So the power input will be supplied to the stator. It is supplied to the stator core. The stator, this is the stator coils, which is I squared R, the stator core, and the rotor loss, which is I squared R of the resistance of the rotor core, which is fixed, and the stator core losses, which is fixed, is always given based on the data, then the friction losses, then windage losses. Now, rotor input is equal to PG, the air gap, the power of the air gap, which is air gap power. So SPG is equal to 3 I squared R2. So rotor resistance is R2. So let's look at this problem here and see whether they can do it based on the diagram above there. A 10 kilowatt, 400 volts, 3-phase, 4-pole, 50 hertz delta connected induction motor is running at a no load with a line current of 8 ampere and an input power of 660 watts. At full load, the line current is 18 amps. Find the input power. If no input power, no, not find. And the input power is 11.20 kilowatts. Beg your pardon. And the input power is that. So this is just the rating of the machine. It can go up to that level. So the state effective resistance per phase is, I think, is 1.2, as according to what I can see. And the friction and windage loss is 420 watts. Therefore, calculate the stator core loss. B, total rotor losses at full load. Number C is total rotor I think that's a friction losses. We shall see what it is at full load, what the shunt losses. Then full load speed. That is the sort of torque there, the shaft torque and motor efficiency. So the starter losses, core losses, is the PS input minus the starter I squared R loss minus the friction plus windage loss. So you see that the stator power, how do they get 1660 here? So you're told that this stator here with the 4-pole is connected to the induction motor, is running at a no load with a line current of 8 and an input power of 660. So if that is the input power, we shall subtract 420. The friction and windage losses. And how do you get windage loss? No, friction, windage loss is given here. Friction and windage loss is given as 420. How do you get, why do they have 3 times 8 over 2 times square times 1.2? So state effective resistance is 1.2. So for you to get the 3-phase, the 3 times I squared. So this This is a line current. So it's 8 divided by root 3, then squared times that, which is going to give you 163.2 watts. So this is the total value. So if you subtract this value from this value you put in, you get 160.2 watts. So this is our value there. So the second question is to look at the total rotor losses at full load. So that is the same as the rotor resistance that is causing the loss, which is I squared R of the rotor, plus rotor core and friction winding losses. The air gap power full load is based on the power of the gap, air gap, and that power is 11,200 minus what we got here. These are losses due to the stator. So 11,200 is the input power to the rotor. So you subtract. So the real power going to the rotor, the real power, this air gap power going to the rotor is 11,200 here minus the losses of the stator. And that one minus again the power that is going to be lost on the resistance. I'm seeing 18 here. So the rotor, the full load line current is, so it is 18 over root 3 times 2 multiplied by the resistance, that is the input current. So you get 1064 8 watts. So total rotor loss is 10,648 minus 10,000, which is this one here. Which is now the loss, total loss is that this small. So the total ohmic loss is 648 minus 420. 420 was given as the windage loss. So we shall get that one as 228 watts. So number D is the full load speed. The full load speed so you must first of all get S. The S. So this expression here will give you the power of the air gap. So you put S, the subject, and PG is going to multiply. So you'll get S as this value. So full load speed of the rotor is 1 over S times 1500. The speed at which you expect the rotor to rotate. If you calculate the speed of the rotor, the synchronous speed, you'll find it is 1500. And you'll find that the full rotor speed is going to be less by 0.02 if you multiply that kind of slip. The internal torque of rotor is the air gap power over Ws. So it's given as that power, which is 1064, 8 by 50 pi. And there is a internal torque. I think power divided by the Ws gives you torque. That is okay. There's so shaft torque. Is a supply power over Ws given by that equation there, which is a slip, and you get that value. So efficiency is the power of the shaft divided by the power of the input. So how much input is taken to the shaft? So it is 10,000 for the shaft divided by 11,200, and you get 0.892. So efficiency of the rotor, the machine is 89.2. So this is just analysis, which I'll give you the notes to go and study more. So let's look also at the equation for the starting of induction motors. So let's look at if it is also there in the PowerPoint. Okay, it appears that equation is not there. Let's just go back to these notes here. Okay, if this is the induction motor, which the rotor is short circuit at the end, the SC, at starting, normally S is equal to 1. The rotor is not rotating. And R2 into S minus 1 over S is equal to 0. That means the load is replaced by short circuit. The mechanical load is replaced by short circuit. This is the expression of the mechanical load. Because R into this equation is equal to electrical analog of the variable mechanical load. And the I starting is equal to V over Z, where Z is the sum for this equivalent circuit here. This and this is real values. This one is a complex variables. So this is sum of this plus these two reflected. This one now reflected secondary. And this is the current to the starting of the rotor. So we'll divide that by that and get is very, very less. This value is very, very small according to the expectation. So the current flowing in the stator can be as large as 5 to 6 times the full load current. So when you sort this area here, these values, they are in 0 point something. They are in micro values, milli values. So when you divide a small value with a big value with a small value, you get high current. Here, shunt branch is neglected, and we just have this kind of arrangement. The shunt branch was supposed to be having something here. This one is no longer is applicable in this case. So it is neglected in this case. So we said it's going to be 5 times what can be expected of actually. So the starting torque now is TS. So the power to the rotor over the rotating frequency. So power to the rotor is always given like this. I starting at R2, which is not variable, over WS. So full load torque at that point, at the starting, is this value divided by WS times the S full load. So S full load is equal to 2 to 8%. So TS starting on over T full load ratios is IS of I full load times squared, that is, according to this expression here, times SFL. I think they're taking these values here. We're considering this. So that is majorly at full load, the torque starting at that starting in the full load is this equation here. We shall see it in the examples on how to do some numerical work and see that is what is going to work for us. So let's look directly now on how do you start squirrel cage motor or rotor, that's case. direct starting. So when the squirrel cage motor is started direct online, IS is equal to I sorting circuit current, which is V over Z sorting. And Z sorting is that equation there. So in that, the static current is equal to short circuit block rotor current. Let short circuit current be S times I full load current. And essence of L, this full load okay, slip is going to be given 0.04, which is 4%. So TS over TFL is, let's say it is 5 times. So it is 5 squared times 0.04, which is 1. So they have to say is 1. This means that when starting current is 5 times full load current, the starting torque just equal to 1. With large starting current, the motor must accelerate at and reach normal speed quickly, otherwise overheating. This damages the motor. The load on the motor at the time of starting must be very low or at no load. The consumer is heavily penalized due to high peak current produced which or while direct online starting. So this starter is not used. Online is not used for motor whose rating is greater than 10 kilowatts. So the starting means that we have to reduce that voltage for starting. So the starting current can be reduced by reduced voltage starting. This causes the starting torque to reduce heavily. Such starting can only be carried on a light load or no load. So there are various methods of reduced voltage starting of the motor. One is stator impedance starting, auto transformer starting, and star delta. So what is it that we can say is a stator impedance starting? The stator terminal voltage of an induction motor is reduced to X times of the rated voltage by including resistors and inductors in the three-phase line feeding the stator. Then V starting is going to be X V short. And therefore IS is equal to X, which is 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 equal to starting current. So X I short. So we're just going to reduce the V sorting, the voltage which was used for sorting, and the I current which was used when we were sorting the circuit. So the torque ratio, starting at the full load, with this one square times S full load. So the starting torque is reduced to X squared times of the full load torque. I know you can be asking why are you squaring these things? This equation here, ratio, will generate the squares. And This torque is obtainable with direct switching. So if you want to just put online switching, you just put directly the system to the plug at the wall. It can work when by reducing the full load current, or maybe by reducing the rating of the voltage that is initially being used to supply the rotor through the stator. We shall see the stator impedance starting circuit. So you must have a circuit for stator impedance starting, which makes this one work by making much cheaper. So the stator delta star is cheaper. The stator delta star, stator delta starter is cheaper than this with better starting torque. So there's a starter which is connected in the stator delta with this kind of terminal reduced rated voltage by using the resistors and inductors. You can also use an auto transformer, which is connected in this. You have the three-phase line, and we have the switching circuit, which is supposed to connect the all phases together at the same time, and a switch here for the circuit, and the rotor is here. So this is a stator now, which is being started using the transformer. This is just like reducing the voltage. The transformer is reducing the voltage. So you can see it is a variable. Instead of having the voltage coming in like full, we step it down. So stepping down voltage means that you have to vary the windings, and you can feed it now to the stator, and that voltage is meant to start the rotor. So V is a line voltage, and I starting is Xi short. So this is a starting current with the full load. It was almost a short circuit, maybe to full load current, SC, the starting current with full load. So the torque S over torque FL is X squared that over SFL. So in this case now, this one is not squared. So S starting for the line is reduced to XL with the ISC, which is ISC starting current with full load. And you see it is, if this is a resistance, or maybe the new configuration, I think X is supposed to reduce. If this is a full load current, X is supposed to reduce that current. So this is on starting current over the full load current. So compared to the stator impedance starting, the line current reduced further by a fraction of X, while the torque remaining the same. The auto transformer starting is much simpler and speedier even to the stator impedance starting. So I think it is just almost a repetition of what we have done there. The last one is the star delta starting. So there's a delta here. The supply is delta supply. The delta is just like a transformer. Then the star part is connected to the star part is now connected to the rotor. Okay, this method of starting is designed to operate normally in delta. The starter winding is shown, the stator winding is shown in the AA. So this is stator now. AA, BB, and CC. Although it's not very clear here. So it makes sense that this method is much cheaper than auto transformer starter and commonly employed for small and medium-sized motors. So here we have the starting, this formula we had it initially, the ratio of the starting, where SM is a slip at the maximum torque. So the other one was the squirrel cage motor, but now the starting of the slip ring motor. And I think now the only thing I can give to you is the notes to read and get understand it better. I think I gave you some assignment to do on the starting methods of motors. I hope you have done the assignment as expected of you, so that we just do the comparison with what we have discussed this afternoon. I'm just scrolling back to see where we have started and what you have done so far today. The power flow diagram there, the rest of the full load, torque and maximum torque equation loads. So the torque slip characteristic equation, characteristic diagram. This is the characteristic diagram of as the slip moves from zero. When the torque is zero, when the slip is zero, torque is zero. So you're moving this way. Or slip can move from high 1 to 0. So this is 1. This is 1. So this is a standstill. When slip is 1, the rotor is not moving. So as the slip lowers down to 0, you'll find that the torque is moving up to the maximum torque. Then as the slip now still lowers down, it will now come down to zero. Also, the torque will reduce. So torque equation now from 1, it moves from, can move from maximum going down. Based on the slip goes down until the end. But this is the equation for the torque equation for the torque characteristic against the slip. You can see there is a, if it is starting at a lower torque, it can move to with the torque climbing. It can move, if it starts with a higher torque, it rises very fast to the maximum and then falls immediately. So medium starting speed or torque is almost going to be maximum at a certain level, then comes down. So for you to achieve, if you start the motor at this higher torque, for you to achieve the max torque, is the slip is at that point. Medium, the slip is at this point, almost 0.6, no, 0.3, some 0.4 something percent. At 0.4%, the torque, starting torque will be almost at this point. It reached maximum at 0.4 something there. If we start at slip of 1, and if you start at slip of 1, but on a lower torque, it will reach somewhere here, 0.2, to reach a maximum at that slip. So I'll post this I have two sets of handwriting written notes here, so it will be useful for you to read and understand. You know, in our course outline, we are supposed to look at the equivalent circuits, rotating field, not really, rotating field, equivalent circuit, parameter determination, maybe those torques and everything, analysis of the operation. We shall look later on starting methods you have just seen, starting currents and its effects on the supply voltage, speed torque characteristics not yet, speed torque curves not yet. We shall let's do the circuit diagram, speed control, rating and heating losses and efficiency. I think we have done a bit of some losses. So these ones are not yet. We shall look at this. We shall look into this. We shall look at application and braking and overload protection of the motors. So almost like we have done some of these things up to here. So the rest of the we'll be discussing this. Then when we are through, we shall look at the the single phase machines, construction.
Quick question, sir. The ones you've labeled X are the ones we shall not cover for the semester, or
We have not done so far,
but we'll do them.
obviously.
We're required to do them.
Yeah, I think they're in. We shall do them in the weeks to come.
Okay.
Yeah, so by week 7 we shall start maybe the single phase machines. But I'm intending to send you the some assignment on this what you have covered today from here. Maybe some kind of anything you discuss today. We shall do the assignment homework. Have you done the homework I gave the other time? Have you posted?
Yes.
Otherwise, I want to send you these notes so that you can read it clearly and at your own time. Then, in case of any question, also you need to send to me directly on my mail. If you have a question individually, we shall share. Or if you have my number, you can write something on the WhatsApp and you ask questions. Is there anything remaining that you have? If you look at the PowerPoint I gave you here, uh, it is not covering the topics as a lot of it is having some assignment and even some problems which have been solved. But you can use it at some point to study the torque slip characteristics. And these ratios are very much clearly provided. I like it up to that point, but I'll also look at some better notes to cover the areas that we need to cover for the next 2 weeks, so that it can also help you solve the assignment. I think that is all for me today. Can we call it a day? Unless there's a question.
Yes.
Yes.
Thank you.
Yes.
Good
Okay.
time. I'll send you some homework. Good time.
Excuse me, sir.
Yes.
Yeah, I had a quick question, a concern. When an induction motor, its ratings, you done a question where it was rated in terms of its power and voltage. So I was asking, when you have, maybe for the example we did, it had a rating of 11 kilowatts. Is that with respect to the rotor, or it's the input power that's given to the motor? Excuse me, sir. I think you are muted.
Okay, what I'm saying, what do you understand by rating from your own maybe layman language.
Yeah, I understand the rating might be the, you might rate it in terms of the voltage that the motor might should operate in. So I think maybe you can rate it in terms of the power output and also in terms of the power input. Sir, you are muted.
If it is rated at 11 kilowatts, 415 volts, and 50 hertz, what does it mean?
I'd say the 11 is the power output. For 15 volts is and 50 hertz is the supply frequency of 450 volts, 415 and frequency of 50.
You mean to say that 11 kV is the output, 50 hertz,
Yeah,
and for 15 volts, 415 is the input. Yeah. Those are the
yes, that's
supply.
just
The supply frequency. Then the 415 volts is the input voltage on the three-phase power at its own rating. It cannot work on maybe 200, maybe let's say 500 volts. Otherwise, it will cause a problem. Then the output of that machine is 11 kV. Is that correct? Okay, no, kilowatts.
yes.
I think you're right. You're very right. So the
And
power,
from the
yes, go ahead.
from the question we did now, it was rated 11 kilowatts. So if you have a rating of 11 kilowatts, that means that will always be the power output. The induction motor will always have a power output of 11. So you work with, it's so efficient that it will always output the 11 kilowatts of power.
Yeah, let's say if you look at that question clearly, which I would want you to go back and look at it, you may find that if you read something at 11 kV and you realize that the losses are also being placed there based on the windage and many other things there, then it is not going to operate at its maximum rating because of the losses, and therefore you may find the efficiency is going to be at 80%. Is that correct? So you're working below the rating, yeah?
Yes.
So below the rating means that you are not efficient. So if you want machine to operate at its rate, which is not very easy, if you're operating at 11 kV and also 11 kV and also you expect to work at 11 kV, then you'll be 100% efficient. Can that be right? Is it if you have a power which you're expected to work on and do your work according to that power, but then you also do it according to that power, then you'll be working on 100% efficiency. But it is not possible because you're using current and you're also connected to other things which are also negatively acting on you. So you may not work to that rating. And therefore, the losses that are being, friction, windage, everything, conductor losses, generating heat. Motors are heated always. Motors need cooling. That's why you need to cool the motors to reduce the heat, reduce the friction by putting a lot of, you put some friction losses. You can put the maybe you can oil it up. You can also put the bushes and many other things to reduce that kind of rotational losses, and therefore it will work efficiently. Otherwise, I think that's a very good question. But all the same, why don't you go back to notes and see and get those data clearly? Why is it 11 given rating, and therefore why? How do you use the rating to get the efficiency? Those two areas are very, very important. By the way, questions that will come in the exam will work on the rating and the losses and all that. That one you cannot miss, because that is why we are doing this thing. Are you together?
Yes, yes. Thank you. I'll look at the question again, the
Thank
data.
you. Somebody is raising the hand. I have lowered it. Now go ahead. Is there any question again there? We may have rushed because of time and because of the online teaching. You want the student to get the maximum. That's why I take a lot of my time to rush over the things there. But it's good for us. It's good for us because learning is not just food feeding. It's just taking a little bit of 20% of your time and going through very quickly so that you can get time to understand. But all the same, induction motors are very, very easy to understand based on the questions which are given and the diagram that are picked, those figures are taken from the diagram, like the equivalent diagrams or the equivalent diagram I gave you there, making it much easier for you to understand. Otherwise, it's one of the areas that are very cheap to understand, and it cannot beat someone who's doing engineering. Any question again? I'll send you 2 sets of notes, handwritten notes. It will help you a great deal to understand. So there